is the video tutorial walkthrough for F325 January 2011. Feel free to skip through the video, look for the black titles that tell you which question you're on, and then you don't need to watch the whole thing all at once. Okay, as we can see, question 1 is a rates question because here we've got a rate equation, so we'll just put a box around that because that's going to become important in a minute. And we've got some data, so we've got some concentrations and we've got an initial rate. Now the question actually asks us to calculate K, so we're going to rearrange the rate equation, so we'll change that to K equals rate divided by those concentrations, and don't forget that squared on the NO. Now that rearrangement will get us our first mark. Then we're going to substitute in those numbers, so the rate is here, concentration of H2 is here, and the concentration of NO is there. But I mustn't forget that that is squared, and that gives us an answer of 83,333. That's our second mark. And then we're also asked for the units, so we've got moles per decimeter per second on the top, and on the bottom of this rearranged equation we've got 3 lots of moles per decimeter, so we can cancel 1. That leaves us with 2 moles on the bottom, so that's going to turn into moles to the minus 2. 2 dm to the minus 3 on the bottom, so that will turn into dm6. And the seconds to the minus 1 is already on the top, so that stays the same. And that is our third and final mark on this first part of question 1. Carrying on down, so I'm just going to remind myself that rate equals K H2 NO squared. So if I double the concentration of H2, this is first order. So whatever I do to the concentration happens to the rate, so that's going to times by 2. NO is second order, so whatever I do to the concentration is squared. So if I half the concentration, 0.5 squared, I'm going to get times by a quarter. And then the bottom one, I will have times 4 for the effect of H2 and times 4 squared for the effect of NO, so times 4 times 16 equals times 64, so the answer is times 64. Okay, continuing with part C of question 1, we've got explain with a reason what happens to the rate of reaction when we increase the pressure. So if you think all the way back even to GCSE, we've got increasing pressure increases the initial rate. Okay, so that one should be straightforward, and that's 1 mark. And then we've got to explain why that happens. So we say because there are more frequent, and I'm going to also say successful, collisions. Okay, and we get 1 mark for that. If you were to look at the map, mark scheme on this, then you would see that you have to get the word frequent in there. So it's really important that you either say frequent or more collisions per second, because if you think about rate, it's the number of collisions in a given amount of time. So that's why we've got to use that word frequent. Coming down to the bottom, we've got what happens to the rate constant. You should all know that the rate constant is temperature dependent, so we say K is unchanged, because what we're changing is the pressure and not the temperature. If we then go down to the bottom of this question and we look at this part, this is where everybody tends to fall down on this type of question. So we've got suggesting a 2-step mechanism. So I'm just reminding myself at the bottom here of the rate equation and of the balanced equation, because I'm going to need both of them to be able to answer this question. So the first thing is, step 1 will be our rate determining step, and whatever's in the rate equation, that's the reactants in the rate determining step. So if you look at the rate equation, I've got 1 H2 and I've got 2 NOs. And then I can make whatever I want out of them, so anything at all. So I'm going to go for N2 and H2O and a half O2. Okay, I'll come back to this in a minute because there's a number of different options there. So now I'm going to compare this to the product side in the balanced equation. So N2, I've made that, so I can tick that off, and I've made 1 H2O. However, O2 is not in the products of the balanced equation, so that has to go down here. So I've got a half O2, and then I look down at the balanced equation, and I've already used 2NO. I've used one of the H2s, but I've got one left, so I put that in here, and then again, from that, I'm going to make 1 H2O. So if I do my counting up again, I've got 1, 2 H2Os, so that can go. I've got an N2. The oxygen cancels out because I've got it in the product side in the first step and the reactant side in the second step. So if I was to cancel that down, I'd be left with 2H2, 2NO making N2 and 2H2O, which is exactly right. Now just sticking with this question for the time being, because if we go back to what I said at the start about the key thing being in this first step you can make whatever you want. So another option would have been to do N2 and let's make that N2O and H2O. Okay, this is also on the mark scheme. So if I look again at that balanced equation, let's just put that back to how it was. Okay, so now I'm going to compare what I've made this time to what's down here. So I've got one of the waters, but the N2O is not in the products of the balanced equation. So the N2O, dinitrogen oxide, has to go down here. Again, if I look at the reactants in the rate determining step, I've used one of the H2s, which means I've still got one to use up, but I've already used both NOs. And then on the right hand side of that, I'm going to make N2 and H2O. And again, final step would be to cancel down, so the N2O would cancel. Obviously don't scribble it out in your real exam. And I'm left with 2 H2s, 2 NOs making N2 and 2 H2O. So you can see there's a number of options, and the examiner will check for a couple of things. One is that your reactants in the rate determining step match what's in the rate equation. Okay, so that will be one. And then the second thing that they're going to do is they're going to check that all of this cancels down to give you the balanced equation, and that'll be your second mark. Question 2 on the 2011 paper is a transition elements question, and we're starting off with a fairly nice electron configuration question. This is really checking your use of the periodic table and the fact that you can go and look up Fe and find that it is number 26. So you're going to complete this electron configuration. So we're going S2S, 2P, 3S, 3P, 4S, 3D. So we've got 10 there, that makes 12, that's 18, that's 20, and 26. Fe2 plus, it's lost 2 electrons. Remember that the 4s electrons go before the 3d electrons, so we're left with 3s2, 3p6, 3d6, and it's 1 for each of those correct configurations. Property of Fe2 plus, other than its ability to make complexes, you need to say either coloured compounds or forms coloured compounds, or you can say it acts as a catalyst. Lots of people on this try and give general properties of metals such as malleable or conducts electricity. You can't get away with them because this is specific to transition elements. If we carry on down, we've got a bit of redox in here, so we're looking at what's being oxidized, what's reduced. So let's start over here. You know that SO4 has a 2- charge on it, so the Fe here is +2. And let's head straight for the transition elements because we know it's them that's going to change. So here we've got sodium's going to be +1, oxygen's -2, which means that the chromium is going to be in a +6 state. Carry on over here, so we'll look at what's happened to the iron. Now we've got 3 SO4, 2 minuses, so that's -6 overall here. And 2 of these, that means that the iron is +3. So we've got iron goes from +2 to +3, which means that it is oxidized. And then our chromium, if we go over here, so SO4, 3 of them again, so that means that the chromium is also +3. So that means that the chromium has been reduced. And then, if you're short on time, I'd leave it like this because I think I've done enough on this equation to get those marks. If you've got a bit more time, write some nice sentences down here explaining that iron is oxidized as it changes from +2 in iron 2 sulfate, to +3 in iron 3 sulfate, and chromium is reduced because it changes from +6 in sodium dichromate to +3 in chromium 3 sulfate. So you could write that down here. If we carry on, then we've got a bit about ligand substitution, and we've got a K-stab question. So you should remember K-stab works very similar to KC, but we leave out the water, so we can ignore that. So we're going to have K-stab equals Fe NH3 6 2 plus. Okay, now this is quite crucial because obviously transition element complexes have square brackets, but we use square brackets in K-stab to indicate concentration. So you must have 2 sets of square brackets here. And equally, when we put in the bottom part of this question, so there's the first set of square brackets, and that's the second to indicate concentration. And then we've got ammonia, which only needs 1, because obviously it's not a transition metal complex, so it doesn't need square brackets around it, and that's to the power 6. So that's our 2 marks for this, because what the examiner's looking for is a correctly written expression and correct use of square brackets and double brackets where needed. Underneath that then, we're on to hemoglobin. And we're obviously going to be talking about ligand substitution. So what we've got to say is that oxygen bonds to Fe2+, and that will get us 1 mark. Okay, so the oxygen's bonding to the Fe2+ in hemoglobin. You might want to say it's a coordinate bond, but that's what gets the mark. And then we're going to say when the oxygen is needed, it is released. And that's the second mark. You could also get away with saying when needed, the oxygen is substituted for that second mark. So either of them will do. So I'll go through that again. A lot of lines for not writing very much. First step, oxygen bonds to the Fe2+ in hemoglobin. Second mark, when the oxygen is needed, it's released, or when it's needed, it's substituted. Either will do. Next, we've got a little bit more on K-stab. So what we're going to be talking about here is the size of stability constants, because we're comparing 2 ligands. So what we need to say is that for the complex with carbon monoxide, K-stab, or stability constant, is greater than for the complex with O2. That's going to be our first mark. And then for the second mark, we need to say this means that the CO bond is stronger. And that's the second mark. Okay, so if we've got carbon monoxide, we've got less oxygen transported by the blood. That's because hemoglobin will preferentially bond to CO, carbon monoxide, And the reason that that happens is that carbon monoxide ligand's got a bigger stability constant than oxygen, and that means that the carbon monoxide bond is stronger. 2 marks. Then we've got platin. So it's a complex of platinum 2, so let's just make a note of that there. PT2+, just in case we need it. And it's got 2 stereoisomers. One of these is used in medicine. Platin is a neutral complex. Explain why it's neutral. So you need to say because platinum is 2+, and 2 times Cl- equals 2-, so the charges cancel out. Okay, the mark scheme is a little bit lenient on this one, I thought, because quite often it's required that you say this, that the charges cancel out. So I'm going to make sure that I put it in there. Now we've got 2 stereoisomers of platinum. So we've got PT, it's obviously square planar. This is one that you should have learnt. So there we are, 2 square planar molecules. This one is, for me, the cis. So that makes this one the trans. And you're going to get 1 mark for each correctly drawn structure. And then the third mark, I'm going to write that down here. You need to say that the ligand forms a coordinate bond with platinum ion. And that's the third mark. Okay, so if we look at what was required in the question again, so draw diagrams of 2 stereoisomers, yep, 1 for each of them, and describe its bonding. Well, describe the bonding is described in these coordinate bonds. So the ligand forms a coordinate bond with PT2+, 3 marks. We've got describe the action of platin in the treatment of cancer patients. Again, this is something you really need to learn, and all we need to say here is that platin binds to the DNA of cancer cells, and that's the mark. Sometimes you'll see that this is 2 marks, and that's because you could also say this stops the cancer cells from replicating. In actual fact, on this mark scheme, they only gave you 1 mark whether you said either of those statements, but I would say both, because sometimes if they're asking you this question, it could be for 2 marks, and you'd need to say both of those things. In part G, so we've got unpleasant side effects of patients. If you were to go into drug research, then this is what would happen. You could start with the current drug and then modify its properties by changing some of the functional groups in it. And then we've got a recent drug called carboplatin, and the structure to carboplatin is similar to platin, except that a single 1,1-cyclobutane dicarboxylate ion replaces 2 chloride ligands in the structure of platin. Okay, so draw the structure of 1,1-cyclobutane dicarboxylate ion. Okay, here we go. So this is what we're going to draw. So we've got cyclobutane. Let's start there. Okay, so you can see that in the name there, cyclobutane. So that's going to look like this. Okay, or you might have started drawing it just like a square, like this. Okay, and then we've got 1,1. So coming off one of the carbons. Equally, I could have put it there because remember, number 1 is going to be wherever the groups are. And we've got 1,1, so that's these 2, dicarboxylate. So these are going to be carboxylic acid groups, aren't they? So let's just start with this and then we'll talk about why this is wrong. Okay, so 1,1-cyclobutane dicarboxylic acid would be this. Okay, but to make a carboxylate ion, remember all we do is get rid of those H's and turn this into an ion. And there we have 1,1-cyclobutane dicarboxylate ion. Next we're going to draw carboplatin. I'll put that up here because it's just going to be easier. So remember, this is the platin that we drew earlier. Okay, and it says 2 chloride ligands are replaced. So I'm going to get rid of them. And we're going to put on those oxygens from the cyclobutane dicarboxylate ion. like this. That's a terrible square, but never mind, because that's going to get me the mark. Now, if you were struggling for which of the platins to use, because if you think about it, if you had gone for this one, how on earth would you get this to sit on these two bonds at 180 degrees? So you couldn't have used that one. And this is the structure you should have ended up with. And it's 1 mark for each of those structures. Okay, so if you were really struggling on this one, it's only 2 marks on your paper. And I would have probably moved on and saved the time to get onto later questions and come back to this. Okay, so that is question 2. And you can see it's 18% of your paper, so well worth spending a bit of time going over this one. But again, I'll just repeat, this question here, drawing these, this was quite tough, so if you were spending a lot of time on that, it's time you could have better spent on later questions in the paper and then perhaps come back to this when you had a little bit of time left at the end. Question 3 on the 2011 paper is an acids question, and we can see that we've got a titration curve. We're told that glycolic acid, and we're given its structure, is titrated against sodium hydroxide. And here we've got the titration curve, so it's starting at about 2 to 3, so that's a weak acid, and finishing up at somewhere around 13, so that's a strong alkali, which is what we're told in the question. Underneath that then we're told to write an equation for what's going on, so we copy down the formula for glycolic acid from the top of the question, and we react it with sodium hydroxide. We're told that it's a 1-to-1 ratio, so we don't need to do any balancing with that. And we should know that we get a salt, so it's the acidic proton of the carboxylic acid group that's going to be removed. And we're going to make that into a salt, and we're going to get some water. Now we're going to determine the concentration of the sodium hydroxide. So if we look up in the question, we've got a volume and a concentration for the glycolic acid. So the first thing we're going to work out is moles of glycolic acid. And we're going to label what we're doing so that it's very clear to the examiner. Okay, so we're going to show all working. And that gives us 0.003125 moles of glycolic acid, and that's our first mark. And then, because it's 1-to-1, moles of sodium hydroxide is the same. It's not actually a mark for this on this mark scheme, but it's very important from your kind of processing point of view to write down the moles of sodium hydroxide again, because sometimes there are marks for writing that even though it's the same number. And then we're going to get the concentration, so we'll do N times 1000 over V. Put those numbers in there. And then the volume, so we deal with the volume by using the graph. So if we look at the vertical section, which is where the end point of this titration is, and we can see that at the end point the volume of sodium hydroxide is 22 centimeters cubed. So we can put that into our concentration calculation, and that gives us a final answer of 0.142 moles per decimeter. And that's the second mark. Moving on to part 3. So we've got a question about indicators. So this is very straightforward for us because we need to say that the indicator must change colour in the vertical section of the titration curve. Okay, so that is what determines which indicator we use. And then we're going to write an acid dissociation constant for glycolic acid. So let's remind ourselves of the structure, which was this. And we've already talked about the fact that this is the acidic proton. So if we're going to get dissociation happening, it will look like this. So now we can write a Ka expression. So Ka, and remember it's the products of the reactants. Okay, so 1 mark for my Ka expression, and the next one we're going to calculate that. So immediately when reading this question, you should be seeing the 0.125 mole per decimeter glycolic acid has a pH of 2.37. So that should really trigger you into doing 10 to the minus pH. So we're going to calculate concentration of H plus by doing 10 to the minus 2.37, and that gives us an H plus concentration of 0.00427 moles per decimeter. Okay. Next, we can rearrange, and remember this is a weak acid, it's not a buffer, so we can kind of approximate to say that Ka is equal to H plus squared over HA. Okay, so we'll just remind ourselves of that there. So if we're going to do Ka, then we put those numbers in. We've just worked out the H plus concentration. I'm going to square that, and the concentration of the acid is up here. And that's going to give us 1.46 times 10 to the minus 4. So far we're getting 1 mark for the H plus. So again, if you see pH, always turn it into H plus. 1 mark for calculating the Ka, and then you can see at the bottom we've got units. So if we look, we've got 2 lots of moles per decimeter on the top and 1 on the bottom. So we can cancel, and that leaves us with 1 lot of moles per decimeter, and that is the 3rd mark in this question. And the final part of this is calculating the percentage molar dissociation of the glycolic acid. So if we look at what we're going to do there, we know that the concentration of glycolic acid is 0.125. We know that the concentration of H plus is 0.00427. Okay, so if you think about that equilibrium which we wrote up here, this is 0.125, this is 0.00427. So what we want to know is what percentage has dissociated and turned into H plus and the corresponding negative ion. So we're just going to work that out as a percentage. And that gives us an answer of 3.4%. Okay, so you can kind of check yourself here, because remember weak acids dissociate to a very, very small extent. So if you'd have ended up with quite a large number there, then that should make you realise that there's something wrong. Part C of question 3 is a buffer question. If you've watched the tutorial video on buffer questions, then this should be a dream for you. If you've not watched that tutorial, then please do go and do that. However, let's have a look at what we're going to say. So we've got a buffer of glycolic acid, and we'll just remind ourselves that that was this. And ammonium glycolate is used in a facial cleanser. So if it was ammonium glycolate, let's look at this now. So that acidic proton's gone, and we've replaced it with an ammonium ion. And we're going to explain using equations how a solution containing glycolic acid and glycolate ions can act as a buffer. So glycolate ions are going to be this. Okay, so make sure you're annotating your question as you're going through so that you can refer back to it, and it will help you structure it. So the buffer will be this, which we've already written in an early part of the question to help us. So that acidic proton from the carboxylate group's gone, and it's dissociated, so that's the buffer equation. And then it says, explain how it can act as a buffer. So if we add some acid, then what we get is we're adding H plus ions, and that's going to react with those glycolate ions, and we're going to get back some of the glycolic acid. And we're going to say that equilibrium shifts left. Okay, so we're adding extra H plus. So if you look at this equilibrium, if we're increasing the concentration of H+, the equilibrium is going to be driven to the left to reduce the concentration of H+. If we add some alkali, so we're adding OH minus ions, they're going to react with H plus and we're going to get water formed, which means that equilibrium is going to shift right. Okay, again, if you look up at that top equation, we're reducing the concentration of H plus because we're reacting it. So this equilibrium is going to shift to the right to restore the concentration of H plus. So if we look at those marks, we've got we've explained how it acts as a buffer because we've given the buffer equation. We've said what happens when you add acid, and we've said in terms of the equilibrium what happens. We've explained what happens when you add alkali, and we've said what will happen to the equilibrium. So we've done that first bullet point, and then we've got how this buffer could be prepared from ammonia and glycolic acid. So what we're going to say is preparation. So glycolic acid will be reacted with ammonia, but very important, we need to say glycolic acid will be in excess so that we get partial neutralization, and we're going to write an equation for that happening. So there's the glycolic acid and ammonia, and we're going to get ammonium glycolate, which we've already written at the top of this question. So we're going to get one for explaining how it'll be prepared, and particularly it's this bit that gets us the mark, and one for the equation. So you can see that's the 7 marks, and I've hardly used half of the space in this question. So again, when you get to these questions and you see lots of lines, don't panic, stick to what you know and write it down. And finally we get on to part D of question 3, and this is where it really does get quite tough. First bit's not too bad, but part E is really quite challenging. So if we look at what we have to do, we've got ammonium thioglycolate. Thio indicates that we've got sulfur in this compound, and it's the ammonium salt of thioglycolic acid. Again, we've been given the formula, and when it's dissolved in water we get an acid-base equilibrium. So we're going to label the conjugate acid-base pairs, and we can see that we've got a pair here, so let's call them pair 1, and we've got a pair here, so let's call them pair 2. And now we just need to add the A's and B's. So if we look at this one, this is the thioglycolate ion, and it's gaining a proton to form thioglycolic acid. So that, if it's gaining a proton, that makes it a base. So this must be the acid that goes with it. And then ammonium, the ammonium ion, loses a proton to make ammonia, so that makes it an acid because it's a proton donor, and therefore that has to be the base. And it's 1 mark for each correct pair. If we carry on down to part E then, so this is really quite challenging as I've said, and it's about hair perming. So we've got hair is a protein, and its shape is the result of cross-linked disulfide bonds. So this is a disulfide bond, and the formula of protein in hair can be represented by this. So RSSR. And I've got permanent hair involves 2 stages. So in the first stage it's wound around curlers, and we've got ammonium thioglycolate applied to the hair, and the disulfide bond is broken. So we've got S, S, and that's being cut. Okay, so we're breaking that bond in the middle there. And it's broken by 2 thioglycolate ions, which is going to be, if we look back up at the top and remind ourselves, it's this one, and we're going to need 2 of them to form 2 molecules containing thiol groups. So if we look at what could happen here, okay, we know we're cutting this bond, so we've just said that, and what we'll end up with is RSH and HSR. So we've got 2 molecules containing the thiol groups here. Okay, so we're going to use RSSR plus 2 of these, and we're going to make two of these and one other product. So let's start writing that first equation now. Okay, so we've written down what we've figured out so far. We've got that protein reacting with two thioglycolate ions, making two molecules containing the thiol group, and then we just need to work out what the other thing is. So, if we look at what's happened, we can see that we gained two protons here, so we must have lost two protons from this molecule. There's no acidic proton here because we're dealing with the thioglycolate ion, so therefore I'm going to say that it's this proton here that's leaving from the thiol group. So if we go with that and say that what's left there will be SCH2COO minus, and this of course needs to form a bond to something else, so the most likely thing is that it's going to join up with the other molecule. So we've got, and we can see we've got a disulfide bond in the middle of this now instead. So if we look back at what we said in stage 1 and just check ourselves, so we're looking here, each disulfide bond is broken by two thioglycolate ions, so we've got this reacting with two of these, breaking this disulfide bond to form two molecules containing thiol groups, that's these two, and one other product. So we've taken off this proton here and we've joined these two together to make a new disulfide bond over here. And then the next bit says, after 15 to 30 minutes the hair is rinsed with a weak solution of hydrogen peroxide. So we know that that's going to go into our stage 2 equation. And it reforms the disulfide bonds that lock the hair in shape. So remember, it was this that was originally the RSSR, and we're going to return it back to its original shape or its original bonding. So we're going to have back the RSSR protein. So we'll put our two RSH molecules into there, and then if we look at what else we're going to get, so what we're doing is we are getting rid of a proton from there, and there's two of them, so we're going to make two lots of water. Now again, what I would say about part E is if you look at it in context, we've got 2 marks out of 100, and if you think about the amount of time that we've just spent talking through this and working these two equations out, you know, you're about 50% of the way through this paper. If you spend so much time on these 2 marks that then means that you don't get to some of the easier marks later on, then it's really not a worthwhile use of your time in an exam. So again, if you get to a question like this and you just really can't figure it out, then you need to move on and you need to come back to this at the end. And like I said, bear in mind, 2 out of 100 marks versus maybe 5 to 10 that you could gain on a later question. It's really worth thinking about your timing. Question 4 is about electrode potentials, and nice starter to this one, which links back to what we were saying about the last question. So the last question was worth 2 marks, took an awfully long time to get those 2 marks, and that might mean that you run out of time on nice, straightforward questions like this, which is worth 3, because all we're doing is drawing a labelled diagram to show the standard electrode potential of one of these cells is measured. Remember, this means the hydrogen half cell. Okay, so if you see, again, exam technique, if you see standard electrode potential, you're drawing the hydrogen half cell, and you should all know that one by now. So you should all be able to draw it. And it looks like this. And we need to label it. So we've got hydrogen gas going in at 1 atmosphere. We've got H plus ions at 1 mole per decimeter. And that's our first mark for correctly drawing that half cell. And if we look at what we're comparing it to, so we've got tin 4 plus and tin 2 plus. Both of these are ions. So we cannot have a solid tin electrode, which would be the most common mistake I tend to see on this question. Put that a little bit closer. Okay, so if we had just tin solid in the equation, then we could use a tin electrode, but we haven't. So we've got tin 4 plus at 1 mole per decimeter and tin 2 plus at 1 mole per decimeter, and we're going to have a platinum electrode, which I just realised I've not labelled on the other one. So we've got our second mark for the correct drawing and labelling of this half cell, and that third mark comes for connecting these two together with a voltmeter and a salt bridge. Again, an examiner will check to make sure you've got no gaps in your circuit and that it's all connected. So our third mark is for a complete circuit. Carrying on down, we've got use the information in the table to write equations for the reactions that are feasible. So let's deal with that. If we look at these, we could have this half equation going forward and that half equation going back. That would be a feasible reaction. So we've got copper and chromium. So let's go and write that down there. If you just remember, whilst we're looking up here, we're going to do this times 3 because there's 1 electron here and 3 here. So if we go down to the bottom, we've got chromium plus 3 lots of copper plus, making Cr3 plus and 3 coppers. That would be our first one. And then if we look again, we could have this reaction going forwards again and this reaction going backwards. And in this case we would need to times this one by 2. So if we write that one down here, so we would have tin 2 plus and 2 lots of copper plus, making 2 coppers and tin 4 plus. And then if we go up here again, so we could have, I think we're done with that one because we've combined it with these other two. There's no scenario in which that would go forwards because these are both more positive than it. So if we look at this one could go forwards and this one would go backwards, and that's our third and final one. Now if we've got 3 electrons in this equation and 2 in this, so we're going to have to go to 6, which is the nearest common number. So we're going to do 2 times this equation and 3 times this equation. Let's go and do that one, and we've got 2 lots of chromium and 3 tin 4 plus, and that's going to make 2 Cr3 plus and 3 tin 2 plus. So there are 3 equations, and we're going to get 1 for every one of those equations. And then we're into, even though these are feasible, so they're feasible because we've looked at the electrode potentials and we said this one will go forwards and this one will go backwards, and we've got a difference in cell potential, in electrode potential. So in theory they're feasible, but they might not actually happen. So we've got 2 reasons. So we might have, we could have non-standard conditions. So that would be our first one. So for example, concentrations not 1 mole per decimeter. So we could have non-standard conditions, and then we could have either activation energy is too high, or we could have the rate is too slow. Okay, so if you're looking at this on past exam questions, it's always 1 for non-standard conditions. I quite like to always say, for example, concentrations are not 1 mole per decimeter, just to be very specific about that. And then the second mark is either one of these two things. So you can't have 2 marks for activation energy is too high and the rate is too slow. It's one or the other. And that's the 5 marks in part 2. And then we're on to part B. And I'm hoping that you'll have noticed there is an erratum notice that goes with this paper because these words are the wrong way around. It won't affect your working if you haven't noticed it, but that's why I've already corrected this question. So the first bit says write an equation for the complete combustion of methanol. So you'll have done lots of these combustion equations at AS level. There should be nothing new around this. And if it's complete, we're going to get CO2 and water, and then we just need to balance this, so we should end up with 2 lots of water, which would mean that we need 1.5 O2. Common mistake is to forget the oxygen that's here in the methanol. Then we've got deduce the half equation for the reaction that takes place at the negative electrode in a methanol fuel cell. So this is the half equation for the oxygen electrode at the positive electrode. And this is the whole cell equation. So basically what we're going to do is subtract this from this whole cell equation. So if we look at what's where, so methanol is not in that half equation. So this is what's going to be reacting. And we can also see that this half equation here doesn't contain CO2. So that's where I'm going to start, because that's how I like to do these questions. So now I'm going to look at, this is in acidic conditions, because I can see at the oxygen electrode we've got H+. So I'm now going to balance this half equation in acidic conditions. So if I've got 4 hydrogens on the left, I'm going to need 4 H+ on the right. And then if I look at the oxygen, so I've got 1 over here, 2 over here. So I'm going to need some water, which then obviously affects my hydrogens again. So I'm now going to make this into a 6. And then that looks balanced to me in terms of atoms. So I've got 4, 6 hydrogens, 2 oxygens and 1 carbon. And then I'm going to need to add some electrons. So if I look, this side is neutral, this side's got 6 positives, so I'm going to need 6 negative electrons to bring that back to being neutral. Then we've got 2 advantages of vehicles using fuel cells compared with the combustion of conventional fossil fuels. So we can have less CO2 is produced for 1 mark, and we can also say they are more efficient. So fuel cells are more efficient. Okay, so notice that I haven't just said they are more efficient, because I'm being specific and saying which one is more efficient, because it's quite important that you get used to doing that. Then we've got one advantage of using methanol rather than hydrogen, so I'm just going to say methanol is a liquid. Okay, because if you remember to what you should have learnt, hydrogen is a gas and it's got to be stored under pressure. Methanol is a liquid, so it's much easier to transport. I'm going to need to say that as well. So it is easier to transport. Okay, so that's the justify bit. So suggest one advantage, methanol is a liquid. Justify it, it's easier to transport. And that's a total of 13 marks for question 4. Question 5 is about entropy. Really nice start to this question again. Sometimes this is given as a table where you have to put the sign. This time we're being asked to explain the sign. So in A, we've got a decrease in entropy. So the sign is negative, and that's because there are fewer moles of gas on the right hand side. So on the product side. Okay, so you can see again we've got 3 moles of gas on the left, 2 on the right, so we've got a decrease in entropy. And then we're going to explain the same thing for B. and in B it says the sign is positive, and we can see that the reaction forms a gas from a liquid. Sometimes we're required to explain that further and say that gas is much more disordered than a liquid, but this one doesn't really seem to mind that we don't say that. In C, so we're going to look at that again, and you can see in C on the left we've got 1.5 moles of gas, and on the right we've got a liquid, so entropy is decreasing, and we're going to say the reaction forms a liquid from gases. And then in D, so let's just look at that before we scroll down a bit, we've got a solid and a gas, 1 mole of a gas on the left, and we've got 2 moles of gas on the right. So we can go back to that gas explanation again and just say that there are more moles of gas on the product side. And that should be a nice easy 4 marks for this question. In part B we're going to be using our delta G calculation, but we can see if we're just looking at this question without actually doing anything, we can see that we've got S values, so we're probably going to be doing SPSR. And let's keep looking at it. So we've got calcium oxide, we've got the equation, we've got delta H, so we know that forwards is endothermic because we've got a positive value there. And then we've got the bullet points, which again, bullet points always tell you how to structure your answer. So we've got the first thing, using the information in the table, show that the entropy change is 0.165 kilojoules per Kelvin per mole. So we've got delta S equals the sum of S of the products, take away sum of S of the reactants, which is SPSR, which we've written up here. I'd encourage you to always write the equation that you're using, because sometimes there's a mark for it. It just so happens in this mark scheme that there isn't, but that doesn't mean you shouldn't do it. So then we're going to do products, CO2, which is 214, and calcium oxide, which is 40. Take away the 89 for the calcium carbonate, and that gives us 165. Remember, that is in joules per Kelvin per mole. And then we've been asked to prove that it's 0.165 kilojoules per Kelvin per mole, so we're going to do 165 divided by 1000 gives us that 0.165 kilojoules per Kelvin per mole. And it's 1 mark for that, because all we're doing is proving it. We've been given the number and we're just proving that that's the case. So we can tick off that bullet point. And then I'm going to show that calcium carbonate is stable at room temperature. So remember, stability comes down to delta G, and for that we're going to be using the delta G equation. So we're going to say 178, which was the delta H given to us in the question. 25 degrees Celsius, you should know, is 298 K, because we add on 273. So we're going to do 298 times 0.165, and that gives us an answer of 129. Okay, very important here that you state your units as kilojoules per mole for delta G, because you could equally work it out in joules per mole, but we haven't done. So you've got to state that, because you get 1 for the number and 1 for the units, and you will also get 1 for the calculation. Then we need to show that it's stable, so we need to say that the reaction is not feasible because delta G is greater than 0. And we get a mark for that, so we're on 5 so far. So now we can tick that we've done that. Next we're going to look at the third bullet point, and you should recognise that if you see minimum temperature, then you're using T equals delta H over delta S. Remember, that's simply a rearrangement of the delta G expression, where we said that delta G is 0. So we've written that and then we've rearranged it to give this. I would suggest just learning this, and whenever you see minimum temperature, you know that you're using that equation. So let's go down here. Again, I'm going to label what I'm doing. So delta H was 178, delta S was 0.165, and that gives me an answer of 1079. So if I am looking at this then, at the moment I don't get a mark for this because I've got the correct number, but I haven't stated whether it's in degrees Celsius or whether it's in Kelvin, so therefore I can't have that mark. So I need to make sure that I'm using the units there. So I'm going to get 1 mark for my answer. I'll also get 1 mark for this rearrangement of the equation. And that gives me the 7 marks for this question. So 1 for proving delta S, 1 for my delta G equation, 1 for the answer and the units. Statement that it's not feasible because delta G is greater than 0, that's another mark. The minimum temperature rearrangement gets me a mark, and the answer complete with units gets me the final mark. Question 6 is a KW question. So not that frequent that you get a big KW question like this. This is quite a nice one though. So we've got a graph showing how KW varies at different temperatures. First thing though is writing an expression for KW, so you should all know this one. For 1 mark. And there we go. The next part of this question, a little bit confusing really, because you all know that hydrochloric acid is in fact an acid, and therefore you'd be looking to use one of your acid calculations. However, what it's actually asking us about is the OH minus concentration, which you might not think about when you're discussing an acid. However, things that you can do with this question. So again, if you see a pH, you're going to be doing 10 to the minus pH. So let's do that first. And that's going to give us an answer of 4.27 times 10 to the minus 5. And that's our first of the 2 marks, in fact. So again, those kind of exam techniques, if you see pH, turn it into H plus, because you're going to get a mark for doing it. So you need to make sure you're picking up on these things, because if you get stuck after that, it doesn't matter. You've got 50% of the marks already on this question. So the next thing, if we look at that KW expression, it says it's at 25 degrees because obviously KW is temperature dependent. But we should know that at 25, kW is 1 times 10 to the minus 14, and that's on your data sheet. So you might be tempted to go up to this graph and have a look, which you could do because kW at 25 is there, and it's 1 times 10 to the minus 14, so no surprises. And then we've got our H plus, which we've just worked out, and the OH minus, which is what we're trying to work out. So all we need to do is rearrange this. And that gives us an answer of 2.34 times 10 to the minus 10. We're not done yet though, because most people will miss this, and it says 2 significant figures, so what we should write down in this final bit is 2.3 times 10 to the minus 10. And that's the second mark. Part B of this KW question, we've been asked to look at whether the dissociation of water is an exothermic or endothermic process. So if we go back to this diagram, and we've got this is our equation, and what's happening as the temperature increases. So as the temperature increases, KW is increasing, which means that it's becoming more dissociated. So as we increase the temperature, this reaction's got a tendency to shift that way. So remember, temperature favours endothermic reactions, so that must mean that the forwards reaction is endothermic. So let's go and explain that over here. So we can say that the dissociation of water is endothermic because Kw increases with temperature. Okay, so just go over that again. This is the reaction as the temperature increases. So going this way, Kw increases, it gets bigger. That means that this reaction is shifting more to the right, which means that temperature favours the endothermic reaction, so the forwards reaction must be endothermic. Carrying on down, we've got determine the pH of pure water at body temperature of 37 degrees. So let's just remind ourselves of Kw. Okay, so let's go back to the graph, because now we need to know Kw at 37, so I'm going to go about here. There is a range on the mark scheme, so obviously you'll have used a ruler, and I'm going to say that's about 2.2 times 10 to the minus 14. You might read it slightly differently, but there is a range. Okay, and looking at the mark scheme, the range says a value between 2.2 to 2.6 times 10 to the minus 14. So I'm right on the edge of it, but I'm in the range, so that's okay. And then we're going to say, because it's pure water, H plus is equal to the concentration of OH minus. And that is only applicable when it's pure water. So if you were talking about an alkali, then that wouldn't apply anymore, but it does fit in this situation. So what we can do is say that that's equal to H plus squared. And so if we want just H plus, which of course we'll need to calculate the pH, then we're going to square root that. So if we put that into the calculator, and my answer is 1.48 times 10 to the minus 7. Okay, slightly different to the mark scheme. If you're following the mark scheme, they've used a value of 2.4 times 10 to the minus 14 for Kw. I'm just showing you that wherever you are in that range, an examiner will follow your calculation through and make sure you've got the right number. So that's what I've got, and I'm going to get a mark for that. And I'm also going to get a mark for correctly reading that Kw value off of something in the range. And then the final bit, if I've got H plus, to get pH I do minus log. So minus log of 1.48 times 10 to the minus 7. And that gives me a pH of 6.82. Okay, so on the mark scheme they ended up with 6.81 because they used a different Kw value. Yours might be slightly different again, because as long as this is in the range of 2.2 to 2.6, then you'll get the answer right as long as you're following the method through. So that's the third mark. And then if we carry on down to the next bit, we've got many experimental measurements use published data such as Kw measured at 25 degrees. Often these measurements have been taken at different temperatures, especially in experimental work carried out at body temperature. What is the consequence of this for the published scientific work? Okay, so if you have a think about what we're saying there, we're using a Kw value measured at 25 to talk about work that's been done at a different temperature, and all we need to say is that the work is not valid. Okay, because if you are using a quoted value at one temperature but you're measuring at a different temperature, then that invalidates your work. And then you need to say because Kw varies at different temperatures. Okay, so Kw is temperature dependent, so you cannot use a quoted value for 25 and then do your work at 37, because that will invalidate your work. I'm moving on then So the reverse reaction of dissociation of water is called neutralization. And then we're going to plan this experiment to measure the enthalpy change of neutralization. Now this is quite a nice question, but people tend to get very thrown off by the number of lines and the freedom in this as well. So it's quite off-putting for a lot of people when they get to this question. So we're going to take this quite slowly. What we're going to do is we are going to mix an acid and an alkali. So an acid and alkali are reacted with each other. That's going to be my first point. So for example, I could do 25 centimeters cubed of 1 molar HCl reacted with 25 centimeters cubed of 1 molar sodium hydroxide. And then I'm going to measure the temperature at the start and at the end of the reaction to find, I haven't got a delta sign, but delta T. And then I'm going to calculate the energy change by using Q equals MC delta T. And then I need to say that M is the mass of solution used, C is the specific heat capacity of water, and delta T is the temperature change. And then I'm going to say to find the enthalpy of neutralization, which is per mole of water, use delta H equals Q divided by N. And then we need to say that so saying if the temperature increased, which it will do because it's a neutralization, delta H is negative. Right, so let's have a look at where we're picking marks up on here. So we get 1 mark for discussing the fact that we're mixing an acid and an alkali. I could actually have missed that first bit out and just gone with this and said what I'm doing, and I'd have still picked that first mark up. However, I thought I'd split it down. So next mark is for talking about the amount. So this is where lots of people get lost, because this text here doesn't tell you to use HCl and sodium hydroxide, but I just decided to pick an example. So it says plan an experiment. So you've got to kind of think, right, if I was going to measure the enthalpy change of neutralization, then what would I do? So you can't talk in general terms because you're planning an experiment. So it's 1 mark for actually stating the amount of the acid and alkali. Then we need to talk about finding delta T, so we're going to measure the temperature at the start and at the end. And then all of this here gets us the 4th mark, so we're going to give the equation and we're going to explain what all those letters mean. And then 1 mark for saying how we're going to scale that up to be per mole of water, so delta H equals Q over M. And then the final mark comes for saying this: if the temperature increased, which it always will do in a neutralization, then delta H is negative. And that gives us the 6 marks for this question, which you can see down there. final two parts of this question. So we've got, this is to do with enthalpy of hydration, and it's the size of enthalpy of hydration, so we're going to use CRAS. Remember, charge, radius, attraction, size. Okay, now we're comparing potassium and rubidium. They are both in group 1, so they're both 1+, so we don't need to mention the charge. So if we look at what we're going to write for this answer, we're going to compare the radius. So K plus, remember that is higher up in the periodic table, so it's going to have a smaller ionic radius than rubidium ion. Okay, so really importantly that you're either saying K plus or the potassium ion and Rb plus or the rubidium ion. If you talk about potassium or potassium atoms, then you're going to lose the marks, but that's the first mark anyway. And then we've got, so we've done radius, then we're going to do attraction, so K plus has a greater attraction for F minus, and we can stick with that actually because we're talking about enthalpy of hydration. We can say K plus has a greater attraction for water molecules. So we're going to say attraction and then size. So Kf has a more exothermic lattice enthalpy, and K plus has a more exothermic enthalpy of hydration. Okay, so that's the first couple of things that we're going to say. Obviously I've put more sentences than there are marks, but I'm covering all bases here. So I've dealt with the radius, that's in this first sentence. Attraction, remember we're talking about enthalpy of hydration, but we're also talking about ionic compounds, so I'm going to say both things. So K plus got a greater attraction for the F minus ion. It's also got a greater attraction for water molecules, which means that Kf's got a more exothermic lattice enthalpy, I might want to say than RBF, and potassium ion's got a more exothermic enthalpy of hydration than the rubidium ion. And then the final one, which is the only bit that's a little bit difficult, but you've just got to learn it really, is that enthalpy of solution is affected more by the size of lattice enthalpy than enthalpy of hydration. Okay, so marks, we're going to get 1 mark for this statement. We're going to get either 1 mark for either of these, and we're going to get 1 mark for either of these statements. So you can see I've said it all there, and although not every one of these sentences get a mark, it's kind of clearly spelling out what I need to say. And then this last one, so what we're doing is we're linking together enthalpy solution with lattice enthalpy and hydration, and you've just got to learn that the solution is affected more by the lattice enthalpy than the enthalpy of hydration. Looking at the last part of this question, so we've got, you can read all the text yourself, but we're talking about dissolving ammonium nitrate, and we're talking about spontaneity. So if you see the word spontaneously, you know you're looking at entropy and delta G. Okay, so that's the first thing to state. If we're talking about dissolving, we've got a solid turning into a liquid. So let's start writing the answer to this question. So we're going to say that during dissolving, entropy increases Okay, and that's because we've got a solid turning into a liquid, so we've got an increase in disorder. And then we need to go to that delta G expression, so we can say that delta H take away T delta S. I should probably write that, it's an easier way of doing this. So delta H minus T delta S is negative. Okay, so a couple of things there then. Let's just get rid of that for now. So 1 mark saying during dissolving entropy increases. So what we need to then say is if it says it's spontaneous, then we know that delta G is less than 0. So we need to say delta H minus T delta S is negative, and that's our second mark. Total of 20 for this question, so 20% of the paper. Question 7 brings us to our redox titration for this paper. So we can see that it's about dissolved oxygen concentration. We've got an initial concentration in which the river water is reacted with Mn2+, and then the key bit to kind of notice down here, we've got iodide turning to iodine, and then iodine reacting with thiosulfate and turning back to iodide. So this is a redox titration, and you should recognise it as the thiosulfate one, and you should also know that the colour change here is from brown to white, although I don't think that's asked in this question. Carrying on down, we've got some data. So we've got a volume for the river water, but then we've got a concentration and a volume for the sodium thiosulfate. So if you get to this question and you don't really know where to go with it, then you could at least work out the number of moles of thiosulfate by doing volume times concentration, that's 0.001, divided by 1000, and that gives you 2.46 times 10 to the minus 5 moles. Okay, so that's your first mark, and then after this it gets slightly more complicated. So if we look up here at these ratios, because we're going to start skipping through these equations now, so we know the moles of thiosulfate. To get the moles of iodine, I'm going to divide by 2. That number will go straight up here, because remember we don't ratio in between equations. So if I know the moles of iodine, and then I'm going to go for the moles of manganese hydroxide, so I'm going to times by 2. That number goes up here, and then to get the oxygen I'm going to divide by 4. So that's quite complicated, so let's run through that again. Okay, so we know that thiosulfate is 2.46 times 10 to the minus 5. If I was going to get moles of iodine, it's 2 to 1, so this would be 1.23 times 10 to the minus 5. That number would be the same up here, and then I'm going to ratio to get manganese hydroxide, because that's the thing that's in both of these equations. So that's times in by 2, because we've got 1 to 2. That puts us back to 2.46 times 10 to the minus 5. That number goes up here, and then I'm going to, because remember, even though we've got 2 here and 4 here, there's no ratioing in between equations. This one is a 4 to 1 ratio, so I'm going to divide that by 4, and that gives me 6.15 times 10 to the minus 6. Okay, so that's the hardest part, I think, of this question. So I'm going to do moles of oxygen. And remember, if you get that wrong, you're going to get errors carried forward. So we do 2.46 times 10 to the minus 5 divided by 4 gives us that 6.15 times 10 to the minus 6 moles of oxygen. And that's in 25 centimetres cubed. And that's mark number 2. We want the concentration of oxygen, so we're going to do N times 1000 divided by V. So we do 6.15 times 10 to the minus 6 times 1000 divided by volume, which is 25, and that gives us 2.46 times 10 to the minus 4 moles per decimeter. That's mark number 3. Now the next step, we don't want it in moles per decimeter, we want it in milligrams per decimeter. Okay, so essentially you can ignore the decimeter because that's staying there, so we're going from moles into milligrams. So the first thing we're going to need to do is go into grams. So grams of oxygen in 1 decimeter, so we're going to do M equals N times MR. So we've got 2.46 times 10 to the minus 4 times the MR of O2, which is 32, and that gives us 0.00787 grams per decimeter. Remember that 1 gram equals 1,000 milligrams, so we're going to times that by 1,000, and that gives us 7.872 milligrams per decimeter, and that's the final mark in this question. Part of this paper, so we've got a comment on whether there's enough oxygen for the fish to survive. If we look back, it says for the fish to survive it needs to be at least 5 milligrams per decimeter, so we're going to say that we worked it out as being 7.872 milligrams per decimeter, and that is greater than 5 milligrams per decimeter, so the fish can survive. You get errors carried forward in this, so if your answer on the previous question was less than 5 milligrams per decimeter and you said the fish couldn't survive, you'd still get that mark. In part B, we've got nitrate 3 ions interfering with the method because they can oxidise iodide to iodine, and we get a colourless gas being produced with a molecular mass of 30 grams per mole. So if we look at this, we can make things we could make out of nitrogen and oxygen. We've got N2, O2, NO, N2O, and NO2. Okay, and if we added all them up, so we've got 28, 32, 30, 32, 36, 46. Obviously this is getting even bigger, so the answer is this one here, nitrogen monoxide. And then if we go down to the bottom, we've got, write an equation for the oxidation of aqueous iodide, so I minus to iodine, because if we're going to oxidise it, that's what's going to happen, by aqueous nitrate 3 ions, so NO2 minus, that's these up here, and we're saying it's aqueous, so we've got some water in there. This says colourless gas is produced, so the NO needs to go in here, and we also get hydroxide ions. So all I've done so far is write down all the information that I've got in this text up here, and that's the first mark for just getting the species correct. Then I've got to deal with balancing this equation. So if we look at what's happening, I'm going to start off by putting 2 there for the I minus, and for the hydroxides I'm going to put a 2 there because water is going to give me 2 taking oxygen from there. And then if I look at that again, so I've got 2 I's, 1 N, 1 N, 1, 2, 3 oxygens, and I've got 1, 2, 3 on this side. Hydrogens, I have got 1, 2, 1, 2, so that's all fine and it's looking good at the minute. But if I was to look at the charges on this side I've got 3 negatives, and on this side I've only got 2 negatives. Okay, so there is a problem in the charges there, so I'm going to have to use a different method for balancing, and that's why this last mark's a little bit tougher. So I'm going to use the redox method of balancing. So I've got I minus going to I2, so this is changing by 1 electron per iodine, and then the nitrogen is going from +3 to +2, so this is changing by 1 electron per N. So I need equal numbers of iodine and anything containing nitrogen, so I'm going to have to increase that to 2 and this to 2. So that sorts out the redox balancing bit. Now I'm going to go back to normal balancing. Okay, so let's look again. Let's put that 2 back to being what it was like. So now I've got 2 iodines, 2 iodines, 2 Ns, 2 Ns, 1, 2, 3, 4, 5 oxygens on this side, 1, 2, 3, 4 on that side. So let's try changing this to 3 OH minuses and see if that works. Okay, so iodine and nitrogen was okay. 1, 2, 3, 4, 5 oxygens on that side, 1, 2, 3, 4, 5 on this side. Try the hydrogens. 1, 2, 3 on this side, but only 2 on the left. So we're going to have to increase the number of waters, which again is going to change things for us. So now we're going to have to include another OH minus, and we'll have our final check, I think. So 2 iodines, 2 iodines, 2 nitrogens, 2 nitrogens, 4, 5, 6 oxygens, 1, 2 and 4, that's 6 oxygens, 4 hydrogens and 4 hydrogens, so all the atoms are fine. This side we've got 4 negative charges, this side 4 negative charges, so that is our final balancing, and that's the final mark on this paper.